Some mirrors aren't plane, but are rather curved or called spherical mirrors, because the curves can be seen as a sector that forms a part of a hollow sphere. The radius of this spherical sector, which passes through the center of the mirror and lies along an imaginary line, extending in both directions, is called the principal axis. This is a line joining the center of the sphere, marked C, known as the center of curvature, to the center of the mirror, P, known as the pole. The radius of curvature is the distance CP. Now we can decide whether to have the reflecting surface on the inside or on the outside. When the reflecting surface is on the outside, it is known as a convex mirror. Another name for a convex mirror is a diverging mirror. This is because parallel rays of light incident on its surface are seen to spread apart after reflection. The rays diverge as though they were all produced from a point F behind this mirror. When the reflecting surface of the curved mirror is on the inside, it is called a concave mirror. I use the word cave to remember that this one goes inside, like a cave, right? This is also known as a converging mirror. That is because parallel rays of light incident on its surface converge, which means come together, to a point F in front of the mirror. This point F, where rays are seen to converge or seem to diverge from on a curved mirror, is known as the focus or focal point. If the incident rays are parallel to the principal axis, like in our illustrations, then the focus lies on the principal axis and is known as the principal focus. The length FP is then known as the focal length, represented by small letter f. Now, what do you notice about the focal points of concave and convex mirrors? In concave mirrors, the light rays pass through the focus, which is in front of the mirror. This means concave mirrors have a real principal focus. And since the light rays pass through there, a real image can be formed at that point. In convex mirrors, however, the light rays only seem to be coming from the focus, which is behind the mirror. And since no light rays actually pass through this focal point, no images would be formed if a screen was placed here. The convex mirror, therefore, has a virtual principal focus. For mirrors that have an arc length that is small compared to the radius of curvature, the focal length is approximately related to the radius of curvature by the simple equation focal length f is equal to radius of curvature divided by 2. You would notice that we used straight line arrows to represent the behavior of light rays on the curved mirrors. This is useful to enable us see how images are formed from these mirrors. Here are a few basic rules to remember when using this convex mirror on your screen. A ray of light along the radius of curvature will be reflected back along the path it came, because the ray will be along the normal to the curved surface. Rays parallel to the principal axis will seem to pass through the principal focus. And thanks to the law of reversibility, that also means that rays that seem to be passing through the principal focus will be reflected parallel to the principal axis. As we have shown also, the continuous straight lines with arrows show the actual path of light, while the dashed lines are virtual lines produced forward or backward. And this is the accepted convention. Like we implied earlier, real images that can be formed on a screen are created when these actual light rays intersect, while virtual images that cannot be formed on a screen are formed by the apparent intersection of these dashed lines. So how do we use these ray diagrams and our knowledge of convex and concave mirrors to know how images are formed? Keep learning to know more.